We will discuss the air wedge experiment. This experiment is very much similar to the Newton's rings arrangement. And the aim of this experiment is to determine the thickness of the foil. So the main apparatus in this instrument is we have a monochromatic source of light and also we have a microscope. Now the difference of this experiment with the Newton's rings is that in Newton's rings we have a glass plate and a planar convex lens, but here we have two glass plates which are attached together at one end, and at the other end we have a foil whose thickness has to be measured.
This is the experimental setup for the air wedge experiment. We have a monochromatic source of light. Usually we use a sodium light for this experiment, and then we have to observe the fringe pattern we have a lens, and beneath the lens we have two glass plates. Now the glass plates are attached as shown in figure. Towards one end it is in contact and the other end we place the thin foil whose thickness has to be measured. And light from the monochromatic source will fall on the lens, and the lens will help the light to fall on the glass plate normally. So the through the air wedge film that is trapped between the glass plates, from there we can observe the fringes when we are viewing through the eyepiece of the microscope.
So this is how you get the fringes. Once you focus with your traveling microscope, you get parallel fringes in an air wedge experiment.
Once you get the fringes, our next aim is to take the reading. For that you should be familiar with the microscope instrument. So we have two scales in a microscope. One is the main scale, from where you can take the main scale reading, and then you have the vernier scale. From there you can get the vernier scale readings.
By rotating the vernier screw, we can change the main scale. Or actually, it is using this vernier screw, we move the position of the crosswire in the eyepiece, and we can bring the crosswire tangential to the fringes so that we can take the main scale and also the vernier scale reading.
So this is the interference pattern that we observe through the microscope. You can see that all the fringes are parallel to each other. Now by rotating the vernier screw, you can move the vertical crosswire and you can place it on any one of the fringes, and you can label it as the nth fringe. And after noting down placing it at the nth fringe, you can mark the MSR and VSR. Now our next aim is that we have to bring that vertical crosswire to the n plus 5th fringe. So that means from n plus 1, n plus 2, n plus 3, n plus 4, and then to n plus 5. So by rotating the vernier screw in one direction, you can bring the crosswire to the n plus 5th fringe. Okay, and then again you can take the MSR and VSR. After moving from the n plus 5th fringe, you can take it to the n plus 10th fringe, and then you can take the MSR and VSR, and from there you can take it to the n plus 15th fringe, and again you can note the MSR and VSR. Now the distance between two adjacent fringes is called as beta, and that is called as the fringe width. To measure the main scale and the vernier scale reading, first I'll show you the enlarged image of the main scale. So this is the enlarged image of the main scale, and before going on to the taking the main scale reading, the first thing we need to understand is about the least count. So least count is defined as the value of one main scale division divided by the number of divisions on the vernier. So you have to calculate the value of one main scale and also the number of divisions on the vernier. Now to get an enlarged image of this main scale, I have shown an enlarged image, and actually the main scale is calibrated in centimeters. Now when you observe the divisions, you can see that the value of one main scale division is 0.1 centimeters. Okay, and also to get the main scale reading, we have a reference 0. The main scale reading is actually the reading that has been completed by the reference 0. So as per our scale, the reference 0 has completed the reading 2.6 centimeter. So in our case, the MSR reading is 2.6 centimeters. Now the vernier scale reading can be obtained from the vernier scale, and we can see that the number of divisions on the vernier is 100. So we can get the least count to be 0.1 divided by 100, and that is equal to 0.001 centimeter. And here also the VSR reading is 45 divisions. Next we move on to the tabular column. As I have told you earlier, we have different orders for the fringes, that is n plus 5, n plus 10, and n plus 15, and so on up to n plus 40. So you can record the MSR and VSR values of all the fringes, and then you can calculate the total reading, that is MSR plus VSR into least count. Now once you have tabulated all the total readings, we are going to find out the width of 5 fringes together. So we can subtract xn plus 5 minus xn. So as you do it downwards, we are actually getting the width of 5 fringes together, and we take the mean of all these fringes together, and that is what you record towards the end of the tabular column. So our aim will be to find out the fringe width of a single fringe. So we can find, you know that the number of fringes n is equal to 5. So the width of a single fringe beta is equal to xn plus n minus xn by n. From there you get beta. Now the length of the wedge is given, the wavelength of sodium light is also given. Now the thickness of the foil, the equation for the thickness is T is equal to L lambda divided by 2 beta. By substituting all the known parameters and also beta to this equation, you can get the thickness of the foil. So that was actually our aim of the experiment, was to find out the thickness of the given foil. So using the equation T is equal to L lambda by 2 beta, we can get the thickness of the foil. So that was our final result. The thickness of the foil is equal to what we have found out from this equation. Thank you.